So, welcome to Zeuthen. I hope this will be a good workshop and you will enjoy it. And we start with the first session. Michał.
Okay, hello everybody. My name is Michał Heller. I'm also kind of a local, but from the other institute, Albert Einstein Institute, across Berlin. I'm very happy to see so many people here interested in tensor networks and high-energy physics at the same time. That's really exciting. My basically personal remark would be to try to keep this meeting as informal as possible, ask lots of questions, and make use of the time for discussions to really discuss physics and try to advance, well, this emerging field of science. So without further ado, let us start with Frank Pollmann from Technische Universität Munich, who's going to tell us about isometric tensor network states. Frank.
Okay. So yeah, thank you for the kind introduction and for the invitation to give a talk here. In my talk, I want to discuss some ideas which I think have, in one way or the other, been floating around in the community. And the idea is to restrict the kind of manifold of tensor product states or tensor network states to a subset that can be contracted or can be worked with efficiently. So the background or the main problems that I want to address with this is to overcome the kind of exponential complexity that we run into when we want to work or solve quantum many-body problems, right? So I'm coming from the kind of condensed matter background, and what we want to solve or what we want to address is that we have, for example, a spin system where we have a number of spins that interact in some way, and we want to understand, for example, what the ground state properties would be. And the most general approach to this problem is, of course, to represent the many-body wave function exactly, right? So we just choose some local basis in these kind of states, Jn, where Jn each goes from 1 to d, like it would go to 2 for a spin 1/2 system. Now we can just write down every state in terms of this basis. And of course, the complexity comes from the point that we have to store all these amplitudes in the many-body wave function, and that very quickly becomes too big to be stored on any computer. And for kind of moderate resources, we can just do a full diagonalization of the problem up to, like, say, 20 sites, and with sparse methods, then up to 30 or so sites. And this is now the goal. We want to use or come up with methods that allow us to go beyond these system sizes. And what I want to discuss in my talk are two things. In the first part, I want to give a brief review of the standard matrix product states, doing this first to kind of introduce the notation that I use, but also because it's the very first talk in this morning, so maybe it's good to have a slow start. And then I want to discuss the idea of these isometric tensor network states. And I want to show that I introduce this ansatz, and also want to show that it is useful in some way, namely that we can find ground states of local Hamiltonians using this ansatz. So coming back to this kind of exponential complexity, so if we express, if we want to kind of express a general quantum state, we can express it in terms of some basis. Again, these Jn are some local basis, and these are now the amplitudes in the many-body wave function. So if we have the state, or like if someone gives to us the state, we can perform a Schmidt decomposition of a state. Namely, we can introduce some bipartition, and the bipartition that I want to have in mind for now is just the bipartition of a chain into two halves, where everything on the left of a given cut is subsystem A, and everything right of this cut is subsystem B. And now we can expand our wave function that we have in terms of a superposition of product states between the left part and the right part. And these coefficients lambda alpha here are the so-called Schmidt coefficients, and the Schmidt states form an orthogonal basis of the left part and the right part respectively. In terms of these Schmidt values, we can then compute the entanglement entropy as a measure for the entanglement between the left part and the right part. Right? I mean, clearly, if the state is a product state, we just need a single term. If the wave function is a highly entangled state, we would need many terms in the sum. And this is now reflected in this entanglement entropy. Good. And all I've discussed so far is rather general. Now I want to discuss the properties of a specific class of states, namely ground states of local and gapped Hamiltonians in 1D. And here we kind of the area law states that the entanglement entropy of a system where, again, we have now a system of length L, we cut into two halves. And if I now look at the scaling of the entanglement entropy as function of a system size, we get a constant. And this is now the area law. Intuitively, the reason why this emerges for ground states of local and gapped Hamiltonians is that in the ground state, the energy is lowered by having kind of local fluctuations of the spins in our system, say, and this leads to kind of the nearby degrees of freedom are strongly entangled, but degrees of freeze that are very distant, like a spin that lives here and some are here, they don't contribute much to this entanglement, and that's why this kind of goes to a constant. So, and with this property, these states are like super special. They're forming like a really tiny corner in this Hilbert space. And now this makes this kind of area law like a really strong statement, because if we are looking for the ground state of a local and gapped Hamiltonian, we just can forget about most of the Hilbert space and only look in this tiny corner. So, and this is tiny corner has now a very nice property that we can use for representing these states in terms of matrix product states, as I want to show in a moment. And the way that we can show it is to look at our Schmidt spectrum, or to look at the magnitude of the Schmidt values. And what I'm doing here is I take a ground state of a local Hamiltonian. Here it's the Ising model, and I calculate the Schmidt decomposition of the state. And what we see is that the magnitude of the Schmidt values decays very rapidly, right? So while I only plot 20 largest of these Schmidt values, there are like hundreds or maybe thousands because the system is sufficiently large. So we see they decay very rapidly, and that gives us immediately a way how to truncate the wave function. We can just throw away, like say here, everything that's larger than, we keep only the largest 20 Schmidt values and discard the rest, and by this we just kind of truncate only a fraction that's smaller than machine precision. And this is something that we can contrast to a generic state. If we just, for example, take a random state somewhere in this Hilbert space, like for example from here, and we just play the same game, we do a Schmidt decomposition, we actually find that the Schmidt decompositions are rather flat, meaning that in this kind of compression scheme that I proposed would completely fail for random states, but it works for these class of area law states. And this is now exactly this kind of idea or this intuition goes now into matrix product states. So in the matrix product states, what we do, we just express the amplitude of a many-body wave function in a product of these rank 3 or order 3 tensors, right? So we have these virtual indices along the horizontal axis and the physical indices on the vertical axis. And if we just multiply or contract all these tensors, we get actually back some approximation of the amplitudes in a many-body wave function. But we have now strongly reduced the number of parameters. Namely, this goes down from something that grows exponentially with the system size to something that scales linearly with the system size. And of course, we have to choose this bond dimension of the matrix is sufficiently large to capture all the entanglement, to capture all the Schmidt states. And one intuitive way that we can bring a wave function into this form is actually to successively performing a Schmidt decomposition at these bonds and discarding the small or the almost zero Schmidt values. Good, right? So the main idea of the matrix product state ansatz is that we just express the amplitudes of our many-body wave function in terms of a product or like a contraction of these rank 3 or order 3 tensors. So now we're getting a little bit closer to what I actually want to talk about. Namely, for matrix product states, we know that we have a gauge degree of freedom. So in particular, if you look at this expression and I just replace my matrices here with some other set of matrices, right? So if I just replace every M by an A, where they're just related by multiplying some invertible matrix X to the left and X minus 1 on the right, we see that this transformation does not change the wave function. It does not change the amplitudes in our many-body wave function. So what it means, we actually can transform our matrix product state just into whatever form we find convenient to work with. And one particular kind of a convenient choice. This is so-called canonical form. And the canonical form means that we can transform our matrices in such a way that they are either sort of left or right isometries. What I mean by this is we take our matrix A, which is, for example, in this left canonical form, means that if we group the indices here on the left, so we group the left virtual index and the physical index together, then we have an isometry of this form. And if we just group the right virtual index and the physical index, then we have like a kind of a right isometry of this form. And in between those, we have now what we call this orthogonality center. And this orthogonality center is now a representation, or like a local representation of our wave function in terms of these sets of orthogonal states. Right? And these are now the states alpha that we get just by contracting everything on the left, and the beta are now the state that we get by contracting everything on the right. And for a certain choice, these alpha and beta, they exactly correspond to the Schmidt states that we had by truncating the system. Right? So for the intuition, like if we just are at site 3 here, for example, then these states alpha, they form now like a kind of a projected basis for the left part. The beta are like a kind of projected basis for the right part, and J is now the local site here. And this form is now very convenient, because like if we have our orthogonality center at this point, now we have an orthogonal representation of our wave function, and we can just manipulate it in the way that we want. And then if we have done whatever we want to do here, we then can shift the center to the side on the right. And the way that we can shift the center is fairly simple. Namely, we can just use a QR decomposition or singular value decomposition to shift the center. So in particular, what we do, we just take our matrix here, which is in the in this kind of right canonical form. We have this lambda L, like the center to the left. And now we just do a QR, and by this we just shift the center to the next side, right? And then we can do this throughout the system. We can shift it left and right and move our center through the matrix product state, and then do optimizations of the matrix product states. And this is exactly what's done in the density matrix renormalization group method. So the short idea there is that we take a Hamiltonian, so this could be our spin chain Hamiltonian, for example, which we can represent in terms of a matrix product operator, right? So now instead of having a single physical index, we have 2, and if we just multiply all these, in this case rank 4 tensors, we have now a linear operator acting on our vector space. So now this is our Hamiltonian, and now we can calculate the expectation value of the energy just by taking the bra and the cat of our trial state that we have at a given moment. And here we have now this orthogonality center sitting at site 3, say. But now we can just take this tensor out, and now this is now a representation of our Hamiltonian in this kind of projected basis. So now we have an orthogonal basis like of this alpha, J, and beta, in which we represent our Hamiltonian, and we can now use any kind of linear eigensolver to find the lowest energy wave function of this. And this is now exactly what the DMRG does. And once we are done here, we can shift the center to the next side, do the optimization, and now do sweeping through the system. And this is giving us eventually then the ground state wave function. Right? So with this, I have basically now a very convenient form of the matrix product state, which we can get without loss of generality. Like every MPS can be brought into this form. And if we are in this form, then we can just get away by solving linear eigenvalue problems for finding the ground states. Good. So far about 1D, and where everything works extremely well. So what about 2D? And if we use exactly this ansatz for 2D, something that we can do and that is also useful to do, we can, for example, put our 2D system on a cylinder and then map it to a quasi one-dimensional model with long-range interactions. However, the problem is if we do this, we find that the entanglement is growing linearly with the circumference of a cylinder, and by this we get an exponential scaling of the bond dimension. So that's that's a little bit of a problem. The question like how to generalize this ansatz to 2D, and just by drawing pictures, this is pretty straightforward, as was proposed by several works before by a group of Nishino and Verschrate, is basically to just add legs, right? Before this 1D structure is just apparent because every matrix has two arms, like one to the left and one to the right. Now one can add these arms and we get this 2D tensor network states. However, the problem is that while they do capture the 2D area law, that if we have a tensor network given, it is still exponentially hard to exactly contract it. And in fact, in order to still have a useful tool, we need then approximate ways to contract the tensor network. So for example, by corner transform matrices or by boundary PEPs, there are many methods that have been proposed to approximately contract the tensor network. However, what I want to propose now is to actually not look at tensor networks in this general form, but restrict the space, and in such a way that it is, motivated by this 1D canonical form. Right? So we recall that we just brought our MPS into a form that everything left of this orthogonality center is in this kind of left canonical form, everything right is in this kind of right canonical form, and we just see that everything from the left and the right just contracts to an identity when we calculate expectation values. Well, this we can now easily draw again in 2D. Right? So now, instead of having just a single orthogonality tensor, we have now some orthogonality rho, and on the left, we have now left isometric rows. On the right, we have now right isometric rows. And that is not quite convenient because we can contract everything on the left and on the right efficiently, right? Because now all these are isometries. We know that if we just calculate an expectation value, this here just gives an identity and that here gives also an identity, right? The convention of these arrows is the same as before, so the arrows always point from the smaller Hilbert space to the larger Hilbert space. And in the middle here, the orthogonality center is now just a standard one-dimensional MPS. Right? So this is now an MPS, and we know exactly how to handle matrix product states. So if we have it in this form, we can now use all the matrix product state techniques that we know and like on this center row. However, and this is now the big question, is like, while for 1D MPS, the canonical form was just a matter of representation. So we can just shift back and forth between MPS in or not in canonical form. Here, this is a restriction. And in fact, we know certain states, like MPS, for example, if we have tensor product states of critical systems, we know that we cannot bring it into this form. However, other states we know we can bring into this form, but in general we don't really have an answer at the moment what this kind of variational power is of this kind of subset of tensor network states. And let me just discuss some more nice properties of the state. So first of all, whenever we draw, like we just take a subset of these tensors with only outpointing arrows, we actually have these subregions have isometric boundary maps. And moreover, there's a certain kind of causal structure in these tensor networks, namely the time flows then opposite to the arrow direction as drawn here. So in order to make this kind of ansatz now some sort of kind of usable or some practical ansatz, we actually need a way to shift the orthogonality center, right? Like we recall from the DMRG method, what make it useful is that we can just do some optimization and shift the center, do some optimization, and then we have some sweeping type algorithm. And here we would need the same. So we need an actual operation that gets us from having the center at a given site to just shift it by one to the next column. And if we were to use the QR or SVD decomposition, that wouldn't work because it would violate the locality and we would not be able to represent the center tensor in terms of an MPS. So what we actually want to do is we want to solve a variational problem. So in particular, we want to minimize the kind of norm difference between having this representation of our center tensor minus having the like a set of like kind of isometric row times a center here. So the way that I've chosen here is that this is some sort of a zero column center, so there are no physical indices on this. And when we have achieved this, or if we just minimize this, this gives us a way to shift the column, right? So note, now the column, like this orthogonality center is on column 2. We just do exactly this kind of splitting operation, and then we attach the center to the next column as shown here. And by this operation, we have now shifted the kind of orthogonality column from 2 to 3. In practice, it turns out doing this kind of minimization iteratively, it works, but it's rather slow. So we actually want to propose some different scheme for doing the splitting, for doing the splitting of this lambda column, and this is what we call the Moses move. And the idea is here the following: so we take our center column, and now we introduce a splitting operation that now successively splits our one column into two columns, where the left column is now the isometry carrying the physical indices, and the right column is just a zero column center. And the way that this splitting is done is by finding a disentangler. And what this disentangler basically does, it decides which kind of entanglement or what kind of fluctuations will actually be channeled upwards and what is going to be channeled to the right. And this is done at each step locally. And then the hope is that eventually this isometry acts as a disentangler on our center column here. Good. Yes? 5 minutes? Perfect. Good. And now we want to benchmark this, because at this moment we don't have any fundamental insights into how good this can work, so we just try it out. And the first test is the following: we just create a wave function on one row. So the way that we can find this is just using standard DMRG, where we have now a high-dimensional local Hilbert space, and now we can use this Moses move operation to peel off this layer by layer, right? So eventually we convert an MPS into a tensor network state. And what we do is we now find the ground state of the transverse field Ising model, and now we just peel it off. And what we plot here is now the entanglement entropy for a vertical cut of the wave function as function of the number of layers that we peeled off. In an ideal world, we would expect that this is decaying linearly, because at each row, each column that we peel off, we reduce the entanglement by a fixed amount. And in fact, what we see is we actually get quite close to this. Like, while initially the entanglement is not really strongly removed, as we go along, we actually see that this, at least asymptotically, appears to approach a linear decrease, which is exactly what we expect if the algorithm works optimally. The second part is that we want to discuss now some numerical tool based on this. And this is what we call the or TBD squared. Right? So as I pointed out before, if we have brought this tensor network into this center column form, we can just use standard MPS techniques. So in particular, we can use a time-evolving block decimation algorithm. So what we can do is we can now take our center column and now apply the imaginary time update, for example, for doing for finding the ground state eventually. And now we just do it on the first column, the second column, the third column, and eventually then we just are done with all the columns, and now we just pull this one up and we do the horizontal ones, and then we just kind of move this red tensor, like the tensor with all ingoing one, once around our square lattice, and then we have performed one complete update. And now we can see how it works as function of the bond dimension. Again, we just take the transverse field Ising model, find the ground state, and we see that compared to exact results, that the energy is actually converging to the exact one as we increase the bond dimension. And this algorithm is relatively cheap in terms of computational cost, so it scales with the bond dimension of the tensor to the 6th power. So it's not that bad. So these calculations were actually done fairly quickly. Good. So this is for ground states, but now we can use the same algorithm for time evolution. And there we have some ongoing work by a student in my group, like Shenzhen Lin, and we just find the ground state, and now we just perform a kind of quench, or we flip a spin, and we then perform the time evolution. And actually we find that it works so far surprisingly well. I mean, we just did some comparison with exact results, and also now just for large systems where we can compare how the results actually converge as a function of the bond dimension. It seems to be quite promising. Good. So with this, I'm coming to the end of my talk. So I introduced some subset of tensor network states that we can very conveniently work with. However, even now it's not clear what really the variational power is of these states, or how large the subset is of states that can be represented in this form. But in our sort of experimental test, we actually find that it does work reasonably well for finding ground states and even doing the time evolution. And with this, I want to thank my collaborators, and this is Mike Saletl, who's at Berkeley, and Shenzhen Lin, who's a student in my group. So thank you for your attention.
Okay, very good. We have time for a few questions, if there are any. Yeah.
So just in regards to the how this ansatz is related to the more general PEPS ansatz. Mm-hmm. So isn't it true that the correlations in this ansatz are a bit skewed? Like, so it's effectively a matrix product state, right, in the vertical direction in some bases?
Mm-hmm. Wait,
so
I mean, yeah.
The correlations in the vertical direction and horizontal directions are, it's going to be exponentially decaying correlations in some direction?
So we assume, I mean, this ansatz can only work if we have exponentially decaying correlation functions, right? So in this we can see that if, for example, you have your tensor network states in this kind of canonical form, and you want to, you would like to look at, or you want to calculate the correlations between the spin that's sitting here and here, you can actually just calculate it from the MPS approach, right? So basically the 1D transfer matrix that you get from the center column would give you the correlation functions, and then of course they can only be exponentially decaying. So this, like I said, this is example where, I mean, I don't know the power of these states, but I know that any PEPS that has, say, power law correlations, like, for example, if you take a 6-vertex model or like Rock-Keevelsen type models, it will not be, we cannot bring it into this form. But reversely, I don't know if every tensor network state that has exponentially decaying correlations can be brought into this form. I mean, that would be a natural and fortunate finding, but I don't know if this is true.
Thank you.
Okay, one more question.
We have very much related question. Is it possible?
Oh, sorry, wait for this because it's a video.
A question that is very much related. Is it possible to actually restore the symmetry over 90 degrees rotation? Because it seems that you put a different, there's some different conditions that the horizontal and the vertical directions have to obey in your construction.
Well, I can write down certain, like if you, for example, take some toric code fixed point states, we can actually bring it exactly into this form, and then it will work. But once we truncate, I don't know.
Yeah. Okay. But you could check this easily when you truncate. You perturb toric code, whether this feature is preserved.
Right. This is what we are doing. We haven't done it yet. But I mean, one thing is also, I mean, like in terms of this truncation, I mean, this is what when we just do this optimization, we actually see the same thing, that if we just sweep without doing anything, we are just going to some certain fixed point of this method. So basically, right? So this is why the energy is going up, right? So we find first, we're just doing imaginary time evolution, and if we were to do this on MPS, we would actually find that this is going down monotonically to a ground state, or to the best approximation of the ground state. But here, since the method itself is sweeping, has this truncation, we see that if basically the pressure towards lower energy states is reduced by having a very small imaginary time step, this is now going up again. But I don't know what this fixed point would be.
Okay, if there are no further questions, let's thank Frank again.